using inspired compliant terminology. So first of all, I work in Minerva Intelligence. It's a startup based in Vancouver, Canada. And we have a software department, a GIS department, and a geoscience department. And we do application both for mineral exploration and for natural hazard. And we collaborate with the Center for Natural Hazard Research at Simon Fraser University. So then, every time it rains in the fall, we have debris flow and landslide blocking a highway and impacting properties. And then during the summer, with increasing temperature, we have permafrost melting and glacier retreating, causing other problems. The World Economic Forum recognized that in the near future, the most likely and with highest impact disasters are related to climate change and are natural disasters. You can see here on the x-axis the likelihood, on the y the impact, and we see different colors. Like for example, the red dots are social risk, the purple one are technological risk, but we see that in the top right corner are the green dots for natural disaster. So we actually have the data and the understanding of the phenomena, but then the scientists often fail in communicating the risk to decision makers, and so then action is not taken and disaster happens every time. What usually happens to assess landslide hazard, for example, is that a landslide specialist is hired and will dig into the literature, will go to the field, and then will write a very thick scientific report written in a cryptic language and will provide a PDF static map. So then when the decision maker has these PDF reports, he doesn't either have the time to understand nor the knowledge to dig deep. And so then there's this gap between the scientist and the decision maker. So at Minerva Intelligence, we put together human knowledge and machine intelligence to provide a better link between scientists and decision maker. So like a human would do, we describe the problem, and we do that using standard, because we need standardized data to have a machine to understand the natural system. So then after describing the data with standardized terminology, we can reason with it, and then we can provide maps. This time will be web maps where you can click and get an explanation of why a polygon is red or green. And then we are also able to advise and say why we got to the specific result. If you want to know more about the background theoretical process we use, semantic network and ontologies, I invite you to stay in this room for the second part of the morning, where my colleague Steve and Jake will dig deep in the theory. But now I want to present you a practical application on AI for landslide mapping. The case study is in Canada, along the Sea to Sky Highway. And this is the homepage of the website, so you can go there and click and explore. The Sea to Sky Highway is in British Columbia on the west coast, and links Vancouver to Whistler, and it goes from sea level to very high mountains with glacier. So it's a very diverse landscape, and there are even volcanoes. So the first step in the process is to describe the landscape. To do that, we need to structure an ontology. So an ontology is a description of entities and the rules that relate the different entities. And so then we have a landscape, and we will describe the different attributes that characterize the landscape, and we use the same attribute to describe landslides. And so then, defining the relation between the different entities, the software is able to understand and infer the relation between the different parts of the system and deliver maps and various products. So then, the first layer we need to take into account is bedrock, because different rocks fail in different ways. And so we took the BC geology map, and we align the terms to the inspired terminology. And then BC has a long tradition in forestry, and so developed a very detailed terrain mapping codes. And in these codes, we are able to store information about the texture, the material, the superficial expression, and the geomorphic process affecting a given area of the landscape. So in this case, we have a steep, hummocky rock slope covered by a thin veneer of rubbly colluvium, and snow avalanche and gully erosion is affecting this part of the landscape. And so then we are able to extract this information and feed that in the machine and let the machine reason with it. So then we have a DM, and we classify based on the slope angle, because steeper slope will fail more likely than less steep slope. And then we have a permafrost and glacier information, because the change in the system is what destabilizes and causes landslide. And so now with higher temperature, permafrost and glacier are disappearing. So then we aggregate all of these different layers, and we produce a vector map where each polygon is described by a semantic network that carry information about the attributes that come from all the different layers. And so then the polygon is described with this attribute. If we read the first line, it has slope, and then there's a value that is, in this case, is steep, and then we have a true-false statement, and in this case, is true. So then we can also deal with negation explicitly, and so we can also say that that specific polygon has superficial material colluvium, and that's false. So then we need to define what a landslide is to be able to find which one of our instances, our polygons, are susceptible to landslide. And so then in this case, again, we use attribute description. So slope is this case is again steep, but we have a frequency term. And so in this case, it's always. And for example, slope gentle, never, because a rock doesn't fall if it's flat. And so then we can compare how similar our landslide model and our map instances are to deliver hazard susceptibility map. And so we go into the reasoning step. So we have aggregated all the different layers into this map polygon described by semantic networks, and we match them against the landslide models to produce landslide susceptibility maps based on the different landslide models. So depending on how similar our instances to our landslide model, we get a score. So the most similar, the highest the score. And so then we are able to have a map where the color are high, medium, and low score, indicating the similarity to each polygon to the landslide model. So then we are also able to explain why that specific polygon came out to be red, susceptible to landslide. Because if we go there and we click on the polygon, we have this panel that comes up, and we can see the name of the model right there. We can see which attribute have been matched, and we can see the score that represents how well the attributes are matched. But then we can go further. We can actually click on the attributes, and we see this matching report, where on this side we have the model, on this side we have the instance, the map polygon, and we can see here the attributes that get matched between the model and the instance. And finally we see the matching report, how many points we got. And if we click on the explanation, we have a short description in plain language that explains why we gave that score to that polygon. Also, we are able to see how the given polygon matches against all the different landslide models, because the same polygon can be susceptible to more than one landslide type. And so we see the models ranked by similarity to likelihood of the best matching, by best matching order. And so then finally we can also give an advice. So when we click on the advice button, again in plain language, we see how the different attributes were And so then we can see if we have further information, we know how we can modify our final output. This type of application relies heavily on the quality of the data. So the better the data, the better the analysis and the result. So now we are planning to develop a system for Italy where landside database has been released recently. DEMs have higher resolution than in Canada, and we have insert, deformation information, and data are beginning to be standardized to the INSPIRE guidelines. So I want to go again over the whole process. So we merge human knowledge into the machine system, and like a human expert, we are able to describe the landscape, to reason about it, to deliver a map, but this time is a web map that is easy to navigate and where we can click and get an explanation on why a given area is so susceptible to landslide, and we can also give advice. And so we hope this kind of application can help bridging the gap between scientists and decision makers. Thank you. I invite you to stay in the room for the second session in the morning and see the presentation of my colleague. And please go click on the Sea2Sky Hazard website. Thank you.
Thank you very much. We have time for questions.
With what other natural hazards it works? You showed the example of landslides, like where you can apply it as well.
Basically, all sorts of hazards. It just depends on now.
The question, please?
Oh yeah, sorry. So she asked, so which kind of hazard we can investigate with this system? And we can investigate all sorts of hazards. We just need to build an ontology and define vocabularies to describe a given hazard. So we can we are actually now working on an open disaster risk reduction platform for Canada based specifically for earthquake. So we can reason about earthquake in the same way. And reason about the hazard and reason about the risk as well if we put the human factor in the equation.
Gio, if you want the users to really understand what you're doing, shouldn't you be also asking the questions that the users will ask? Can you take it the other way and take decision makers' questions, social data, and converge?
Yeah, so
really have a risk.
So this is a hazard exercise, and it's just to showcase what is our capability. But actually, for the Canadian project I was talking about just now, we started exactly like that. We define use cases. We have a use case scenario profile. So see the land manager or the disaster risk responder, and see what are their needs and what they will be looking on a website like that, which information they want to gather, and so then we reason how we can build a platform to satisfy those needs. So yeah.
So it's wonderful to see somebody using the INSPIRE standards, and so just following on from that, have you looked at the natural risk zone model?
We are getting there, and we see how actually we need to implement many aspects in INSPIRE, because for example for landslide, it just gets down to the landslide category. It doesn't go into landslide types, for example, while we need to distinguish between a debris flow and a rockfall if we want to reason about it. So there's a lot of, lots has been done in INSPIRE, but there's still lots to do.
Thank you very much.